This is circuit, no it isn't. What is it? It's digital circuits. And we're in section 10. No, we're not. We're in chapter 10. Anyway, whatever we are. Chapter 10, which has to do with flip-flops. No, it's not what you wear. No, it's not the politicians that tell you one thing and do something else. It's we use it as an electronic term. So the first flip-flop we'll look at is a set, reset, flip-flop. Okay, so we're going to have a set line, we're going to have a reset line. We're going to come into a NOR, and we're going to come into another NOR. And then we're going to come out to a Q, and we're going to come out to a, well, I guess that's a Q naught. We're going to come out to a Q naught and a Q. Q is our real answer, and Q naught is the opposite of the real answer. And then we're going to go in, cross-connect the output of this guy to the input of that guy, and the output of that guy to the input of that guy. That looks kind of weird. All right, well, that's what we got. So that being the case, if I have a 1 on the set and a 0 on the reset, okay, so that 1 comes into the what is this called anyway? The NOR, and 1 going into the NOR or 2 1s going into the NOR. In either case, I'm going to get a 0 out, right? So I got a 0 out. So my Q is going to be 0. And now I've got a 0 out. I got a 0 in here and a 0 in there. So my Q is going to be a 1. So if I have, do a truth table. So if I have a set of 1 and a reset is 0, I get the Q to be 1 and I get the Q naught to be 0. Hence the word set. Okay, we're going to do it again. We're going to go 0 with a 1. And now this guy's 0. Well, this guy's 1. So this guy's 1, making sure he is 0. So because he's 0, I have 2 zeros coming into here, which makes him a 1. So my not Q is a 1. I get a 0 out of this guy, which makes him a 0. So if I go 0, 1, I get a 0, 1. The reset makes it a 0. So now what happens if they're both 0? Okay, so now they're both 0. My both 0. All right. What it's gonna do. It's gonna keep the Q and Q naught wherever they are. So when I apply both zeros, if I'm already at 1, 0, then I get 1, 0 out. If I'm already at 0, 1, then I get 0, 1 out. See how that works? No, you don't. We'll do it again. We'll do it again slower. All right. So before I apply 0, 0, I have a 1, 0 on my output. I apply 0, 0. The 0 comes here. The 0 comes there. It's inverted to a 1, I get a 1. The 1's already here. The 0 comes in. It's a 1, it gets inverted, it's a 0. Okay, I'm going to do it one more time, or 2 more times, or 3 more times. Now I have a 0 and a 1 already on the output. I apply a 0, 0. The 0 and the 1 that's there already gives me a 1, which gives me my 0 back. My 0 and my 0 inverts to a 1, gives me my 1 back. So the 0, 0 is a hold. I'm holding it to where it's going to be. All right, now I'm going to put in a 1, 1. 1, 1. I'm going to erase the other guys for a moment. Erase everything that's there. All right, now I'm going to put in a 1, 1. With a 1, 1, it doesn't matter what it is, I get a 0. And a 1, 1 doesn't matter what it is, I get a 0. Now, how can Q be 0 and Q not be 0 at the same time? Well, it can't. I mean, that's pretty dumb, right? So, but it is. It's both 0 at the same time, 0, 0. But clearly, that's something we do not allow. Do not allow. Because it makes no sense. So, electronically, what we do is make sure we never put a 1, 1 on an RS flip-flop. Okay, so because we get 0, 0 out, and that wouldn't make any sense because Q and Q naught have to be opposite. Okay, do not allow. Invalid. Invalid. If I could spell invalid. But it'd be something that we'd do electronically to make sure we never put a 1, 1 there. And can we think of some circuitry that we could have that would happen? Yeah, we could. Okay. Okay, good.
That wouldn't be the same as a hold then, right?
No, it's not a hold. Because it doesn't matter what it used to be. It could have been 1, 1 to be. It could have been 1, 0 or 0, 1 to begin with. If I put a 1, 1 in, I get a 0, 0 out, and that not used, not allowed. The author used the phrase "not used," so that's being politically correct. Not used, but it's not allowed. It's invalid. Don't do it. Okay, now we're going to do the same thing again. And we're going to have an RS flip-flop, but this time we're going to do it with NANDs. So I got a NAND, I got another NAND, and I've got my Q naught on the bottom this time and my Q on the top. And I've got my set, and I'm going to send my set through a inverter, and I'm going to take my reset, I'm going to send it through an inverter. And then I'm going to cross connect these guys again. Oh, into there. Get in the right spot. And I'm going to say, well, what happens? Set, reset, Q naught. So we'll look at
so they're using NANDs will always be an inverter?
Yep. Yep, you're going to have that inverter there. All right, so I'm sending in a 0, 1. Okay, well, the 1, the 0. The 0, let's see, what's the NAND truth table anyway? A, B, X, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 0, right? All right. So if I send in a 0, I get a 1. If I send in a 1, I get a 0. So if I have a 0, I get a 1 out. If I get a 1 out, then how come I put a 0 there for a 1 out? That's really stupid. Who didn't tell me that? 1. Okay, and then if I have a 1 here and a 1 there, that's going to give me a 0 here. So if I have 0, 1, I get a 1, 0, which is what the meaning of reset means. the Q guy is 0 and the other guy is 1. Okay, I'm going to do it again. I'm going to put in a 1, 0, 1, 0. Okay, so the 1 becomes a 0, the 0 becomes a 1. I've got a 0 going into the NAND, so I'm getting a 1 out. I have 2 1s going into the NAND, I'm getting a 0 out. So my Q is 1 and my Q naught is 0. Okay, we're going to erase those guys and look at what happens when I do 0, 0. Alright, so we have a 0, 0 going in, and before it goes in we have a 1, 0 on the output. So my 0 going in produces a 1, the 1 stays the same, the 0 coming in with a 1 produces a 1? How did I do that? Why am I not getting a 0 out? Okay, I've got a 1 and a 0. I got a 0. Oh, stupid me. As I was saying, the 0 becomes a 1. The 0 becomes a 1. Now I've got a 1 and a 0 on this guy, so I get a 1 out. I've got a 1 and a 1 on this guy, I get a 0 out, and I keep what I had. So it didn't change. I do it again. And this time I start with a 0 up there and a 1 down here. My 0 becomes a 1, my 0 becomes a 1, my 0 and the 1 becomes a 1. I keep the 1. My 1 and the 1 becomes a 0. I keep the 0. So a 0, 0 is going to stay the same. It's going to hold the data. Not going to change. And likewise with a 1, 1, not used. It doesn't make any sense. I would end up getting a 1, 1 out, and so we can't use that one. All right, so now there's 2 different ways. There's more than that. Okay, so now that we've done that, we replace whatever 100,000 gates we're going to use to make our our RS flip-flop with something that looks like this. A box with an S and an R and a Q and a Q naught. Or we could replace it with a box that's S, R, Q, Q again, but now we knot it like that. So we don't care how this thing is made. It's already made. We buy it already made. We're not going to make it from parts anyway. And so that's what we're going to do. And now, what is it going to do? Yeah, we'll forget about it. No. Good enough. All right. Next, we're going to add a gate. So we're going to have a SR flip-flop with a gate. We're going to have a Q and a Q naught coming out. And how are we going to make the gate? Do we care how we make the gate? Yeah, probably not. But if I have a set and I have an AND gate and I got a gate and then I got a reset at another AND gate and I go into my guys like that and I get a Q naught and I get a Q and I cross connect that way and I cross connect this way, then I've got a gated thing, because If the gate's not on, I have a 0, 0 going into that RS flip-flop, and if I have a 0, 0, I'm going to hold it. All right, so I can do that. Now I've got a truth table. Gate, S, R, Q, Q naught. Zero, 0, 0, 0. 0, 0, 0, 1, 1, 0, 1, 1, not used. Q, Q naught. Q, Q naught. Way to go. Stupid guy. Anyway, I don't believe I did that. Knotted the Q twice. It's a back row's fault. Q, Q naught. And what are we calling the 1, 1 anyway? Oh, we could still have Q, Q naught. Because it doesn't matter that I got 1, 1 because the gate's closed. That'll teach me. All right. Now something happens to the gate. It turns on. 1, 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. I have Q. I have Q naught because that's a hold. I reset 0, 1. I set 1, 0. And this guy's both going to be zeros, but I'm not going to use that guy because that makes no sense at all to have both Q and Q naught being 0 at the same time. So now I've got a gated flip-flop that I can turn on. Okay. So what's the difference? Oh, never mind. Oh. This flip-flop can be 1 or it can be 0. What else can be 1 or 0?
On off.
On off. Or
True false.
true false. Or 1 memory bit. So in my first generation computers, when I was making my memory, I made it with flip-flops. It's either going to be on or it's going to be off. I'm going to set it, I'm going to reset it. I'm not going to go, and then it's going to remember. It's going to remember until I turn it off. Once I set it or reset it, it's going to stay that way for a long time. I don't have to refresh the memory. RAM right now, you have to refresh 1,000 times a second, because it's so delinquent in its ability to remember what it is. But a flip-flop like this is going to go on forever. Okay, next flip-flop, D flip-flop. D for Doug. No? So what I'm gonna do is I'm gonna take this set reset flip-flop, and I'm going to have one entry D, and I'm going to come in and I'm going to do that, and I'm going to put that inside another box and just call that a D flip-flop. D, Q, Q naught. So now if my data is at 0, then that's a 0 there and a 1 here, so that makes the Q 0. If the data is a 1, that makes a 1, 0, that's a set, so it makes the output 1. So that's how I do that. I just take an RS flip-flop, throw in the inverter, and now I've got a D flip-flop, and now I put 4 of them on some 14-pin package, and now I've got 4 of them all at the same time. And I call that a data flip-flop. Okay, the data flip-flop could have a clock. Now a clock is different than a gate, but not that much different from the gate. But it is different from a gate. So I could have a D, a Q naught, and I could have a clock. Now, what the clock does is, this is a positive POS, positive edge trigger. Clock, and that if the clock is doing that, so that's my clock, it changes there at the positive edge of the trigger, and that's the only time it changes. So now we're talking in the what was it? The multiplexers and the demultiplexers had to have their timing right. How do they get their timing right? Well, they get their timing right for us using a D flip-flop with a positive edge trigger. This flip-flop's going to change at that positive edge of the clock pulse each time, and now I can get my timing right. Okay? Or I could go and have a negative edge trigger clock, and now I'm gonna trigger on the negative edge of the clock. Negative edge trigger. And I spelled edge different up here, didn't I? Yeah, is that better? Didn't even notice that, did you? I misspelled edge. All right. And then, because I'm such a wonderful person, I can add a set and a reset. Because I can use S and R again for another thing. And so I can have a set and a reset of the D flip-flop. The D flip-flops, the Q and the Q naught, are synchronous. If I could spell synchronous, C-H-R-Y-O-N, no way. Anyway, now, synchronous meaning that they happen with the clock. The set and the reset are asynchronous. They happen at other times when the clock isn't doing what it's doing. Now, where do we get the word synchronous from? What Greek god? Cronus. Anybody remember Cronus, the Greek god? You do? He's the god of time, right? He was the father of Zeus and all the other Greek gods. After he had his children, he decided that this won't do. We can't have more than one god. And so he ate them all, except Zeus. Zeus got away. You did hear the story before, right?
Yes,
of course. Yeah, exactly. Yeah, and so Zeus went and cut Cronus's stomach open, and all the other gods came out. Yeah. So we do remember that story. Okay. So that's where we get the word synchronous from Cronus. Time from Cronus. We had to have some way to, we had to have some science and some way of explaining these things to the little ones, 2,000 years ago. And so it's time to explain it to you guys now, right? So that's how we did that. Yeah, exactly. So now I can set and reset the D flip-flop outside of the timing of the clock. Okay. Everybody believes that. And I can put these guys on a 14-pin thing here. So I got where's my power? So pin 14, I have 5 volts. Fancy that. And at pin 7, I've got the ground. And then at pin 1, what I got at pin 1? I have the reset of data 1. And at pin 2, I have data 1. And at pin 3, I got the clock pulse 1. And at pin 4, am I going to run out of room? 4, I've got the reset of data 1. And at pin 5, I got Q. And at pin 6, I have Q naught. 1, 1. And then on the other side, I have another D flip-flop with the same things on the other side. And in your digital circuit lab, you get to wire one of these up and figure it out, so it'll be really cool. And it'll go up and down. Okay, we turn the page. I'm on page 442 now, and we find the word asynchronous and synchronous spelled correctly. Notice that? The author is so clever doing that, unlike your instructor. All right, and then we have a truth table. All right, so we'll redo the truth table. Reset, set, reset, not. The clock pulse. The data. What Q is. What Q naught is. Okay, so I'm low on the set. I'm high on the reset. So it doesn't matter what the clock is doing. It doesn't matter what the data is doing. Because I'm low on the set naught, that becomes a 1, and I end up setting the Q to a 1. I'm high on the set. I'm low on the reset. That means the reset is active. It doesn't matter what the clock is doing. It doesn't matter what the data is doing. I get a 0, 1. Outside of time, it's happening. They're both low. If they're both low, that means they're both high. If they're both high, I'm setting and I'm resetting at the same time. That sounds bad. Okay? So I end up getting both these guys high at the same time. I better not allow that to happen. We shouldn't be doing that. All right, now we're both low. We're both high, which means they're inverted, so they're both low. So I'm not doing anything there. I have a positive clock pulse happening. The data is high. I get high, low. They're both high. The clock pulse, positive clock pulse is happening. Data is low. I get a low, high. Okay, and that's how this guy would work. In time and outside of time, doing things because he likes it. Okay. Moving past the VHDL stuff. And now we come to the JK flip-flop. JK flip-flop. Now, set and reset, RS, right? SR, set and reset. JK. Who made that up? What does that mean? J and K, I mean, that's like I, J, K, the imaginary numbers in the X, Y, and Z coordinate system. What is going on here? Anyway, I did an extensive search of my office to figure this out, and I couldn't figure it out what J and K stood for. I did a search of the internet to find out what J and K stood for. No one knows. It's lost in antiquity. So it must be Chinese or Japanese or Indian or something, right? But it has nothing to do with the English language being called JK flip-flops. The difference with a JK flip-flop is I've got a J, I've got a K, and I got the Q, and I got the Q naught. If I'm both 0, I'm doing a hold. So whatever it is that I had, I keep. Well, that's what I did with the RS flip-flop, right? 1, 0 is the same as a set. 0, 1 is the same as a reset. But the 1, 1 gives me a toggle. So if I had a 1 here, it goes to 0. If I had a 0 there, it goes to 1. So now the 1, 1 is now something that is allowed, and I get a toggle associated with it. So a 1, 0, I get a set. A 0, 1, I get a reset. And a 1, 1, I get a toggle. Now I'm happy. I don't have anything that I'm not using. All right. Now, how do we do that anyway? We do that with two RS flip-flops. RS, Q. Is it Q and Q naught on the bottom? Q naught. RS, Q, Q naught. And we're going to have a J coming in and a K coming in, and there's going to be a clock pulse associated with the JK flip-flop. So I come in through an AND, I come in through an AND, and now I got time. I go into the master RS flip-flop. I take the clock pulse and I invert it. And I send that in to two other ANDs into there and there, and I bring Q into the top one and Q naught into the bottom one, and then I get my Q and Q naught coming out of here. Okay, well, does this work? That's the issue. Okay, so if I have 1 and a 0, then I have a 1 and a 0. Then I'm setting 1 and a 0. My clock becomes the clock pulse. Okay, I clearly, the clock had to happen, right? So the clock's happening. So I came up, my clock is now 0 because it went up, right? Is that a clock pulse? That's a clock pulse. Sure is, but it's really a gate. This guy's designed to be a gate. So this guy's 0. So if that guy's 0, then nothing gets through here. We're 0, 0. It looks like we got a hold. What the heck happened? Why can't I make it work? What's going on? No one's going to tell me? Oh, you mean I have to make it up myself? Okay, I got to make it up myself. Before there was a clock pulse, what was there? There was a 0, right? Which means there was a 1 sitting there before there was a clock pulse. So now the clock pulse happens. I get a 1, 1. This 1 is still there. That 1, 1 goes through there, giving me a 1, 1, a 1, 0. 1, 0. So we have a timing issue here. And when you do this in multisim, and you make this up in multisim, what you're going to end up doing is you're going to end up putting another 10 inverters here to delay the 1 from becoming a 0 until it makes it through. Okay? When you do it with real equipment, it's easy to do it with real equipment because it's going to work just fine. But when you do it in multisim and it's trying to simulate the situation, you're going to need a longer time delay in order to get through that to make it work. Okay, so remember that, or not. But Paul has not done the digital circuit lab until this semester. His first 3 years here, he taught this class, and I did the lab. So he's not going to know to tell you to put those extra inverters in. Okay, because he hasn't seen that yet. I know. And then the half the class that isn't here hasn't seen it yet either. All right, we call this guy the slave. But you do see that if the clock pulse goes high and this one goes low and this is 0, 0 on those ands, then nothing gets by it. You do see that, right? In which case this is going to be a hold because I got a 0 there, 0 there, but I'm supposed to go through. How am I going to go through? And clearly whatever's here is going to be slower than one lousy inverter, right? Whatever's there for the, I mean, the inverter is going to take as long time as it is to get through that AND. So anyway, that's where that is. JK flip-flop. The JK flip-flop looks like what? Here we go, JK flip-flop. J, K, clock. Q, Q naught. J, K, clock. Clock pulse. Q, Q naught. So there's three of them. J, K, negative clock pulse. Q, Q naught. So there's three different JK flip-flops. It could be more of a gate. The clock pulse in this case is acting as a gate. Here it's acting as a positive edge trigger. There it's acting as a negative edge trigger. All those things are possible, depending on which one you buy. It also has, instead of having a set and a reset, and so we'll draw it again, J, K, clock, pulse, we'll show it with a negative edge trigger, it's going to have a preset, PRE, normally knotted, and it's going to have a clear, CLR, normally knotted. So it's not going to have a set and a reset, it's going to have a preset and a clear. What's the difference? Absolutely nothing. Totally nothing is the difference. We just added different words to your vocabulary to have it mean something else. You can buy it as a knotted guy, or you can buy it without the knot. They come both ways. Q naught. Okay. Integrated circuits. So page 458, we see two JK flip-flops sitting on a 16-pin chip. And here they call it reset and set. Isn't that lovely? Thank you very much, Robin, for being here. So no, these are JK flip-flops with resets and sets. And then on the next page, it shows JK flip-flops with presets and clears. All right. We have synchronous inputs. J and K are synchronous inputs. And we have asynchronous inputs, the preset and clear. All right. So what can we do with the JK flip-flop? Oh, and we could make a JK flip-flop into a D flip-flop by just connecting the J and K. Well, let's see. What are we going to do? Going to have a clock pulse. And we'll make J and K are both 1. And we're going to put a Q there. And Q naught here. And we're going to come into another JK flip-flop. J, K, Q, Q naught. And then we'll come into another one. J, K, Q, Q naught. Is that enough? That's probably enough, right? And then we'll take the clock pulse and send it there. And send it there. And send it there. And we'll start with these guys sitting at, call this guy Q1, Q2, Q3. So I got Q1, Q2, Q3, and they're all at 0. The clock pulse happens. What happens? Well, I've got 1 and 1 on this guy, right? So he's going to do a flip-flop. Boom. But I've got 0, 1 going into them, so he doesn't change. He doesn't change. Okay, see that? Yes? No? Okay, so the clock pulse happens. I've got a 1, 1 there. That's a toggle. So this guy's going to toggle the 1. But you can't toggle the 1 before the clock pulse makes this guy do what it's supposed to do. There was a 0, 1 here. That 0, 1 there makes a 0, 1 here. And there's a 0, 1 here already. The clock pulse makes a 0, 1 there. But this guy gets toggled 1, 1. All right, next clock pulse happens. The 1, 1 gets toggled. Boom. 1, 1, 1, 0. The 1 gets toggled to a 0. Boom. But I have a 1, 0 sitting there. That's a set, so he gets set. Nothing happens to him. Clock pulse happens again. He toggles. He stays the same. He stays the same. Clock pulse happens again. He toggles. He stays the same. He toggles. Clock pulse happens again. Toggles. I missed something. I don't know what it is. I don't know. Hold on, one more. Clock pulse happens again. Both of these guys toggle. Yeah, that's better. Clock pulse happens again. It happens again. It happens again. Happens again. Boom, boom, boom. So I just counted. I just made a counter that counts 1, 2, 3, 4, 5, 6, 7, and then goes back to 0 by using 2J. Did I not? This is the most significant bit. That's the least significant bit. I got 0. I got 1. I got 2. I got 3. I got 4, 5, 6, 7, 0 again. Yeah. I'm going to do it again. That was so cool. I'm going to have a negative edge trigger. Anything going to change on a negative edge trigger? I don't know. We won't do that. We'll wait until next time. Okay. Am I done? And octal VJK flip-flops. Bunch of computer simulation guy. It looks like it's time to do problems. And they're going to be really simple because we didn't do anything, right? We just have, yeah, they're not going to be so, they're going to be so simple it's going to be pathetic. Let's see, 10-1. 10-1. Make the necessary connections to the 7400 quad NAND gate IC and figure below to form a cross NAND SR flip-flop of figure 10-2. Remember that an inverter can be formed by a NAND. Okay, so we're going to go back to figure 10-2, which is back at page 300 and something probably. Nope, 400 and something. Well, why don't we just go get it? Because I don't have to go back to that figure because I already did it, right? So where's my NAND guy? Okay, so here's my NAND guy. So we will highlight him, copy, and put him over on this new page. Okay, so I don't have to go looking for him. I already got him. Edit, paste. Okay, so there he is. We're going to erase the stuff that's irrelevant, like there, there, and there. Okay, and then I'm going to go and say I've got to do it with NANDs. So I'm going to erase that guy, and I'm going to put a NAND there. I'm going to put a NAND here. Okay, excellent. Then I'm going to put pins down so I know which pins I'm using. All right, so I'm going to come in, pin 1, pin 2, out pin 3. I'm going to go in pin 4, out pin 6. I'm going to go in pin 13, in 12, out 11. I'm going to go into 10, and then I'm going to go out through 8. And then I'm going to take pin 6 and bring him around to 9. And I'm going to bring pin 8, and I'm going to bring him into 5. Okay, so that's what I'm going to do. That's my plan. Now I'm going to go and take my thing here, and there's pin 14, and it's going to be VCC, and then here's pin 13 and 12. So I'm going to hook up R to 13 and 12. And then I'm coming out of 11. Right? And then I'm taking 11. I have 10 next to 11. And 9 next to that. And then 8 next to that. Okay, I'm going to get rid of whatever this is here because I don't want it. And then I'm going to hook up pin 11 to 10. And then out of 8, I'm going to have Q naught. Okay, now I look at the other side, and I got pin 1, and pin 2, and 3, 4, 5. I can count 6, 7. I'm going to ground pin 7. All right. Okay. Okay. So now I'm gonna have my set guy go into 1 and go into 2. Then I'm going to come out of 3 and I'm going to go into 4. And 5 is going to come over from 8. And 6 is going to be my Q, but 6 is also going to be going into 9. 6 also has to go into 9, so 6 is going to come around and go into 9. Okay, so now I've taken a, what is it, a 7400 Nan. I guess I should go and draw these guys in there too, and I've turned it into a SR flip-flop. Alright. Couldn't do that on day 1, but today, after going through chapters 1 through 9, that was a relatively easy thing to do, right? Relatively speaking. The third row is trying to convince himself whether or not I'm right. Other than that, we're okay. Number 2. 10-2. Want me to go back to that one so you can look at it more, or? Yes? No? Okay. You're good? Okay. Number 2. Sketch Q. Alright, so I've got a gate. How many do I need? 1, 2, 3, 4. 1, 2, 3, 4. I guess that's too many. Alright, so there's my gate. I've got a S. Okay, we're going to go and going to draw lines down on my gate so I get my timing right. And I really ought to use the, those things are silly, right? If I use these guys, so if I use the dotted lines, I'd be okay. Yeah, that looks pretty good. Someday I'll figure this out. Oh, that sounds good. Yeah, okay. Back to what we're doing. We've got some set. So the set's going to start high, drop down, go on the other side, go up and down, come way over to here, go up again, go down in the middle, and go up and down there. Sort of like that. And then the reset, well, we'll use blue for reset. Reset, gonna start low, it's gonna go high, it's gonna stay high to there, it's gonna go down, it's gonna stay low to there, it's gonna go up, it's gonna go low again, and the timing right there and the timing right there is the same. And what we want to know is, what is Q doing? Okay, so if the gate's off, Q doesn't change. Alright, but right here I have a set and the gate's on, so I'm going to start high. As soon as the reset happens, I'm going to go low. I'm going to stay low. I have to stay low until the next set. Once I get low, I can't go up again. So at the next set going high, I'm also, my gate's on, so now I'm going to come up and go high. I'm going to stay high. Now there's a reset there, but it can't happen because the gate's low and I'm going to be the same through there. But as soon as the gate goes high again, I'm going to reset, and then I'm going to set again. And then the gate goes off. Okay, want me to do that again? Okay, I'm going to erase it. See if I get the same line twice in a row. Alright, so I start off, I got a set going on, the gate's on, so I'm going to be high. Then the set goes off, the reset goes high, so now I got a reset. Okay, the gate is off, so Q stays the same, it can't change. The gate is off, the set's not reset, there's no set, so it can't go up. The gate's off, can't go up. As soon as I get to this gate, the set is on, the gate's on, I go high. I stay high through there. I'm still going to be high because the gate's off, and I'm going to stay high because the gate's off. As soon as the gate goes on again, I see that there's a reset, I go down. Then there's a set with the gate on, I go up, and there's nothing to reset it after the final set. Okay, good enough? One more time? No? All right, not one more time. Okay. 10-8. 10-8. All right. Shouldn't be a problem, right? 10-8. I got a D flip-flop. I want to show the pattern. Okay. So I got my gate. Okay, so my gate's going to start high, go low. I got 1, 2, 3 more highs. 1, 2, 3 more highs. And I got a data guy, and he's going to start low, and he's going to go high. Then he's going to go low, and in the middle of the gate he's going to go high. And then in the middle of the gate being off, he's going to go high. And then he's going to go high, and then he's going to go low, and then he's going to come up again, and then halfway through there he's going to go low. Okay, and I want to know what Q is. Alright, the gate's on, so Q's off until the data's set. the data is set, the gate goes off. Nothing can happen to it until the gate goes on again, and then data goes down. Data's going to go up and down because the gate's on. I'm down. It doesn't matter that data went up because the gate's off. Now the gate's on, data's high, so I'm going to go high. I'm going to stay high. I'm going to stay high. I'm going to stay high until my data goes down. When the gate's down, gate's on, I'm going to be like that. Okay, so if the gate's on, my data can change. If the gate's off, the data is going to hold whatever it is and not change. All right, well, that looks pretty weird. What do we do next? 10, 10. Looks like we're doing it over again the same way, only different. All right, see if I can handle that. What happened? All right, so we're looking at 10, 10. The logic symbol is for a transparent D latch is given before with the inputs E and D. What's so transparent about this D latch anyway? What does the E stands for anyway? Anyway, so I got E. E is enable, in case anybody was wondering. 1, 2, 3. I got 4 highs. I'm going to be high. 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 I'll go down again. And then I got a D. D is going to start low, go high, go low, go up and down. I think I already did this. And then down, and then up and down. All right, and we want to know what Q is. Okay, the enable's on. D is going to be, Q is going to be low. It's going to stay low. It's going to stay low until there, and then we're going to go up, and then we're going to stay up until there, and then we're going to go down. We're going to stay down until there, then we're going to go up. We're going to stay up until we go down, and then we're going to go up and down, and that's what it's going to look like. Sounds like okay. 10, 15. Do I really want to do 10, 15? Yeah, I probably do. 10, 15.
So we're like a week ahead right now?
No, not really. We're on schedule. Okay, 10, 15. I've got a clock pulse. I don't know if I can put all this on one piece of paper. 1, 2, 3, 4. 1, 2, 3, 4. Okay, I got 4 of them. 1, 2, 3, 4. But I don't continue after that. Okay, now we're going to put our lines on because we can. 1, 2. All right, I got that. Now I've got my set knot. I'll use that color. Set knot. All right, and I'm going to start low, and I'm going to go high. Well, that was good. And then I've got my reset data knot. I'm going to start high. I'm going to go up and down there. I'm going to go up and down here. going to stay high. Then I've got my D. I'm going to start low. I'm going to go high. I'm going to go low. I'm going to go high. I'm going to stay high. And that high happens there. I see that I have a positive clock trigger. So a positive clock trigger means the only time D can change synchronously is there, 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 and there. It doesn't matter that the clock is high the rest of the time, because it's only on the positive clock trigger that it can change. Okay, now we're looking at Q. Okay, my set is low, which means it gets inverted to a 1 and I get setted. My reset is high, which means it's a 0, which means it doesn't get resetted. So I'm going to start with high. So I'm high on my Q to begin with. And the only time I do an asynchronous reset is over here, so that's the only thing I'm going to look at. Okay, so I'm high to start with. The positive edge trigger happens. D is low, so I go low. Okay, nothing can happen. R naught is high, S naught is high. Those ones become zeros. I can't reset, I can't set, so it's not a problem. I move over and I see at the next positive edge trigger, my D is high, so my Q goes high. I move over and nothing that the D changes is irrelevant. I now have a reset occurring. So the reset happens and I drop low and I stay low until the positive edge trigger, at which time D's high, so Q's going to go high. I'm going to move over. I see I got another spot where I go low because I get reset. I come over to the next positive edge trigger. I see D is high. I go high, stay high the rest of the time. Okay. So anything, what are we going to remember from today?
J and K doesn't mean anything.
No, you're going to remember that there's no class Tuesday
Or Monday.
or Monday. Yeah. Well, what?
Affect Q in any way?
Where?
The waveform. How did D affect Q?
Yes, D affects Q. So when the positive clock pulse happens, if D is high, then Q goes high. Yeah, when the positive pulse happens, if D is high, Q goes high.
Right.
If the positive pulse happens and D is low, then Q goes low. Yeah, exactly. So D and Q are, D is a synchronous thing. It's controlling Q synchronously when the clock pulse happens. The set and the reset are asynchronous. They happen whenever they happen.
But the reset, when it happens, that also caused the Q to drop?
Yes, the reset would cause the Q to drop or remain at 0. The set the Q would go to 1 or stay at 1. Yeah. All right, with that, we'll call it a day, because our back row has indicated that we may be slightly ahead of schedule.
Yeah.
We really aren't, because you know I have to review everything a week from today anyway. But we're almost ahead of schedule.